I am going to see if I'm not logged out. I was working with a student from Calc 2 right before you showed up. Let me see if I can go back. It doesn't matter. The book is the same, but I hope I'm not logged out, please. Oh, I'm not logged out. Okay. So this is in section 5.3, I want to say. And let's choose problems and just differentiate. That's all we're going to be asked. Yes, there are slightly more difficult situations. Before I continue, I just want to make one other item clear. This must be a constant. What if it isn't? I will have examples in a moment when it isn't. Okay. Okay, here it is, 5.3. Use the fundamental theorem of calculus, part 1, to find the derivative of the function. So from 9 through 20.
Lucky number 8.
Lucky number 8?
Or 18.
18. Lucky number 18. Let's do that. Perfect pick. I'm on page 5. And we're looking at lucky number 18. Where are you, 18? So y equals or g of x is the integral from 0 to tangent x from e to negative t squared dt. Did I copy from 2 problems? No, I did not succeed to do that this time. Good. So we can only, so don't look at this and try to solve for anything. There is no possibility to do that. We're only asked to differentiate this side and differentiate this side. All we have to do is plug this function in here instead of t. Yes, we have to square it and multiply by the inner function prime. This is a constant. I don't have to do anything. So I have to write e to negative tangent x everything squared because it's t squared and now t is tangent. And I have to multiply, since you picked the same thing, multiply by the inner function prime. This is it. There is nothing else that we have to do here. And what did we show? We showed that differentiation and integration are inverse operations. By differentiating the integral, we get the function.
Got it.
Yes, we're going to have more sophisticated examples, but let's choose another. Anything else? And then we'll look at other problems.
20.
Okay, so let's look at 20. Let me copy it. So the integral from 1 over x to 4 from the square root of 1 plus 1 over t dt. Okay, and this is g of x. Or y, same thing. Well, I do have an issue here. The requirement is that the lower limit must be a constant, any number, I don't care what it is. It's not coming into play anywhere, any number. And the top limit can be anything, any function, not a number, of course, because then I will be 0 when I differentiate, because this will be a number. A number prime will be 0. So it's just one situation. It's not a function. So the lower limit must be anything but a constant. The upper limit can be any function before I differentiate. So then,
okay.
Is there anything we can do here?
You just swap them?
Yes, exactly. Awesome. That's all I needed you to say. So square root of 1 plus 1 over t dt. Now we are ready to differentiate. So g prime of x will be negative. instead of t, I plug in 1 over x, 1 over x, and I flip. So I have the square root of 1 plus x times, it must be times the inner function prime. And that's why yes.
Is it -1?
Yes, this is very important. It's a very important rule. That's why I emphasized it for months. Of course, when we multiply, I will get the square root of 1 plus x over x squared. And this is done. We're only asked to differentiate this function using fundamental theorem of calculus part 1. We have to set it up so we can differentiate. And when we differentiate, the integral, of course, the integral with dt, these two are together. When I differentiate, these two go away at the same time. Why? Because when I differentiate an integral, I get the function back. Now we can look at slightly more sophisticated problems. So let's see. So this is use part 2. We've done this, so we can also go back and do more. This is, again, we've done all this. It's part 2, finding the derivative, finding the antiderivative and plugging it in. We've done all this. We can go back and practice, and we'll do that Wednesday or even today if we have time. But what I want to continue with is more sophisticated situations, and I'm getting to them in a moment. 67, 68, 69, 70, and 71. Find the derivative of the function. This is still part 1. So, allow me to choose the first one. I will choose 67, and then you choose the next.
Okay.
In 67, we have a function, g of x, which is the integral from 2x to 3x, from u squared minus 1, u squared plus 1 du. Okay, I cannot differentiate this. Why? Because the requirement is this can be anything. I don't care. But the requirement is that I will not be able to differentiate unless the lower limit is a constant. So this needs work before I'm allowed to differentiate it. And I just want to remind you one of the properties of the definite integral. The integral from a to b from f of x dx is the integral from a to c from f of x dx plus the integral from c to b from f of x dx. In other words, the interval a to b can be split. So instead of finding the integral from a to b, I can find the integral from a to c plus the integral from c to b. This is the property we have to apply here. But you can say, but how do I split the integral from 2x to 3x? Nobody cares. So if I have 2x to 3x, I can split it at a number. I don't even have to indicate what number it is. I don't even care what it is, because it's never coming into play. If you want to put zero, put 0. If you want to put 100, put 100. If you want to put -5, put -5. It doesn't matter. I just like to put the number sign. So then this integral changes into, I'm on page 6. So this integral changes into 2x to whatever you want to put in there. Plus, it has to be the same. If you put 10, you have to start at 10. If you put 15, you have to start at 15. If you put 0, you have to start at 0. To 3x, u squared minus 1 over u squared plus 1 du. This is ready for differentiation, but this one isn't. How do I make this one ready for differentiation?
You turn that one into a negative.
Exactly.
Flip it.
Finally, I'm ready to find g prime, and this is what I need to differentiate. When I differentiate the sum of two functions, I differentiate the first one and I differentiate the second one. So let's differentiate the first one. I have to copy the negative sign in front. What do I do next?
You plug it in all the variables.
So in u squared, when I plug in 2x, what do I get?
4x squared.
Very good. Times the inner function prime. Excellent. Plus, how do I write this one?
9x squared minus
Exactly. 9x squared plus 1 times the inner function. That's it. Leave it alone. You don't have to do anything else. Done. So this is as hard as it can get. It cannot get harder than this. So I have to remember two properties. One property is when I swap the limits of integration, I have to change the sign in front. And the other property, any integral can be split. Where do I split? How do I know what's between 2x and 3x? Nobody cares. As long as I split it, because when I differentiate, this goes away as being 0. Because when I plug this in and then differentiate, it will be 0 anyway. So this does not mean anything, but it has to be here, and it has to be at the lower limit, and it has to be a constant. That's it about fundamental theorem of calculus part 1. Please choose another so we have another example, and then we'll move on to the other two leftovers.
I guess 70.
Very good. Let's take a look. We have f of x equals the integral from, I think I see the square root of x to 2x, and arctangent t dt. Perfect. Perfect pick. Great job. Okay. The same situation. I have to work on this before I differentiate it. And since we already know the mechanism, we will have the integral from the square root of x to whatever you want to put in there, arctangent t dt, plus whatever to 2x. And I have to flip this one, and then I'm ready to differentiate. Oh, dt plus full stop. And now I'm ready to differentiate. And that's it. It's just the concept that we are practicing here, that the differentiation and integration are inverse operations. So f prime of x. So negative in front. I have to replace, by differentiating, all I'm doing is I'm writing arctangent t, replacing t by the square root of x. But I have to, because it's not plain x, I have to multiply, and I'm differentiating. So this is the inner function, this is the outer. So I have to differentiate the inner function. And when I differentiate the square root of x, I get 1 over 2 the square root of x. And this is done. And now plus. I replace t by 2x. Arctangent 2x times the inner function prime, which is 2. You can leave it alone. Do not attempt to simplify anything. This is it. Any questions? Do you think we should look at other examples? Or is it clear?
I think it's clear.
Okay. So now let's take a look at the other two leftovers. One that I would like to continue with